Today in this lecture, we are going to see the mock test analysis for physics. So here is another question. A proton carrying 1 mega electron volt kinetic energy is moving in a circular path of radius r in uniform magnetic field. Okay, so r is the radius. What should be the energy of an alpha particle to describe a circle of same radius in the same field? Okay, so first there is a proton carrying energy 1 mega electron volt, and then we have an alpha particle. Okay, so what should be the energy of the alpha particle? That is what we have to find out. Options are 0.5 mega electron volt, 4 mega electron volt, 2 mega electron volt, and then 1 mega electron volt. Okay, so let's look at the solution. When a charged particle carrying charge q and mass m is projected in a uniform magnetic field B with velocity v, then it experiences a magnetic force. Okay, due to this force, it starts to move in a circular path. Okay, the required centripetal force is provided by the magnetic force actually, because we know for any particle to perform circular motions, there has to be some centripetal force, and in this case it is provided by the magnetic force only. Okay, centripetal force is equal to magnetic force, and the standard formula for centripetal force is mv squared upon r, and magnetic force on any charge is given as qvb. Okay, q is the charge, v is the velocity, and b is the magnetic field. Okay, then from here we can say r is equal to m upon qb into v, isn't it? We have just arranged this equation. We can see this v, and over here one v cancels, and after arranging we get r equal to this equation. Okay, now let's say that k is the kinetic energy, and kinetic energy is nothing but 1/2 mv squared. Okay, this is the standard formula as we all know. Okay, now over here, from that equation of kinetic energy, we can write v square is equal to 2k upon m, and therefore v is equal to under root 2k upon m, and therefore after putting this value of v, okay, this v in the equation of radius r, it will be m upon qb under root 2k upon m, because if you remember, this formula was mv upon qb. Okay, so we have just put the value of this v over here. Okay, now what we have done is we have taken this m into this roots, so we have to make it squared, and therefore this m and this m will cancel, and only one m will remain over there, and therefore under root 2 mk upon qb, that is going to be the radius. And now what we can do is we can just arrange this. What we will do over here is we will square this whole equation. After squaring, what we get is k equal to qrb whole squared upon 2m. What we have done over here is we have squared this r squared equal to, this root will be gone, 2mk upon qb whole squared, and we have taken this on the other side, then taken this 2m on the other side in the denominator, and what we get is the value of k, that is kinetic energy. Okay, now for a proton we can write over here kp, the kinetic energy of the proton, it is equal to ERB. You can see it was QRB, but what we have done is we have put the value of Q, because we know that proton is positively charged with the charge equal to E, that is 1.6 into 10 raised to minus 19 coulomb, but it's positive. Okay, and m is equal to mp for proton, that is mass of proton. So we have just put the values for proton over here, and this is the kinetic energy. Okay, now similarly, for an alpha particle which has a mass 4 times the mass of proton and twice the charge, we can write over here this equation, k alpha is equal to 2e. Here you can see, instead of just 1e, we have put 2e because it has got twice the charge, 2e rb whole squared upon 2 4 mp. Okay, 4 times mp because it has got mass 4 times. Okay, and after arranging this and cancelling out few terms, what we get is this ERB whole square upon 2 mp. Okay, now dividing 2 by 1. Okay, so if we divide this equation by that previous equation for the proton, what we get is this. We get 1 only. That means what? K alpha is equal to Kp. Kinetic energy of alpha should be equal to kinetic energy of proton, and it is 1 mega electron volt that is given over here. Okay. So, therefore, the correct answer in this question is going to be option D, that is 1 mega electron volt. Okay. So, that is the correct answer. So, here is another question. The distance covered by a body in time 5.0 plus or minus 0.6 seconds is 40.0 plus or minus 0.4 meters. Determine the percentage error in the speed. Okay. So, over here if you look at these numbers, over here we can see that the uncertainties are also represented in both of these quantities. First, time is also uncertain by this much amount, and then distance is also uncertain by this much amount. Determine the percentage error in the speed. Options are 13%, 14%, 15% and then 16%. Okay. So, let us find out the solution. First, S is given and this T is also given to us. Okay. Now, velocity or the speed we know V is equal to S upon T. 40 upon 5 will be 8 meters per second. So, this is okay and this is fine, but we also have to find out the uncertainty in the answer. Okay, because we want percentage error. Okay. Now, we know the standard formula. Okay. Over here we can see V is equal to S upon T. That means what we have done over here is S is divided by T. That means over here we have performed a mathematical operation of division with two quantities having some uncertainties, and in that case the maximum value of relative error is delta V upon V is equal to delta S upon S plus delta T upon T. These are the relative errors. So, whenever two quantities are divided, then the maximum relative error in the answer is always the sum of the relative errors in the respective quantities. Okay. So, therefore, this is going to be the formula. Now, what we can do is we can put the numbers. Delta S is given, S is given, delta T is given, T is also given. Putting all these numbers, we get 0.13 over here. But what we want is percentage error in the speed, and therefore, percentage error is equal to delta V upon V into 100. Okay, this is just relative error. When we multiply relative error with 100, we get percentage error. So, it is going to be 13%. So, that is the correct answer over here. So, over here option A represents the correct answer. Okay. A train moving at a speed of 220 meters per second towards a stationary object emits a sound of frequency 1000 hertz. So, we have a train that is moving at 220 meters per second. Some of the sound reaching the object gets reflected back to the train as an echo. The frequency of the echo as detected by the driver of the train is what? Speed of the sound in air is 330 meters per second. So, it is given. Options are 5000 hertz, 3050 hertz, then 3500 hertz and then 4130 hertz. Okay. So, this is what we have to find out. So, we have a train that is moving at this speed 220, then it is actually emitting some sound waves towards a stationary object and the frequency is 1000 hertz. Now, what happens is some of these sound rays are reaching, they are actually reflecting back towards the train as an echo. The frequency of the echo as detected by the driver is what? This is what we have to find out. So, the solution is very simple. First of all, let us say that small v is the speed of sound, u is the speed of train, okay, and f is the original frequency of sound. Okay. Now, v is given, that is 330, then u is given, that is 220, and f is also given, that is 1000 hertz. Now, first case is this one, train moving towards the stationary object, isn't it? Train moving towards stationary object. So, here train is the moving source of sound and the object is the stationary listener, isn't it? So, since the train is moving towards stationary object, the apparent frequency as received by the object is f dash, let's call it f1 dash equal to f naught, the original frequency, into v upon v minus u. This is according to the Doppler effect. Okay, this is according to the Doppler effect. f1 dash is equal to f naught into v upon v minus u. Okay, now hence the stationary object will receive sound with frequency f1 dash and hence the same frequency is reflected by it. Okay, it will reflect the same frequency. Now, case 2 is this one, sound reflected by the object and received by the driver in the train. Okay, now in this case what happens is the stationary object is the source of sound sending sound of frequency f1 dash towards the driver. So, in this case what will happen? Over here the driver is a moving observer, in this case moving with speed u. Okay, so this is the second case. Now, what happens over here is the apparent frequency as received by the driver in the train is this one, f dash is equal to f1 dash v plus u upon v. Again, this is according to the Doppler's effect. Okay, now what we will do is we will put that equation of f1 dash from there over here, and then after putting, what we get is this, f1 dash is f naught v upon v minus u, and this is v plus u upon v. V will get cancelled, and what we get finally is this equation, isn't it? And now what we will do is we will put all the numbers. Original frequency is 1000, v is 330, u is 220, and over here also 330 minus 220, and after solving what we get is 5000 hertz. So, f dash is going to be equal to 5000 hertz. Okay, so this is the frequency of sound as received by the driver in the train. Okay, so the correct answer is going to be option A, that is 5000 hertz. So here is another question. In a coil of resistance 10 ohm, the current induced by changing magnetic flux through it is shown in the figure as a function of time. Okay, the magnitude of change in flux through the coil in Weber is what? So here you can see we have got current on one side and time on the other axis, and this is the graph of how current is changing with respect to time. Okay, so here we can see this is 4 and this is 0.1. Okay, now options are 6, 4, 8 and 2. Okay, so these are the options. What we have to find out is the magnitude of change in flux through the coil in Weber. Okay, this is what we want to find out. So over here few things are given, like the resistance is given. Okay, so we can find out the change in flux. So let's look at the solution. Here it is, this is the diagram. Then we know EMF is equal to I into R. This is the standard formula. Therefore, I is equal to EMF upon R. Okay, but EMF is equal to this formula also, that is d phi by dt, and it is equal to I into R, and therefore d phi is equal to R into I into dt, isn't it? From this equation you can see, if we take the dt on the other side, then d phi, the change in flux, is equal to R into I into dt, and therefore phi, if we want the phi, we have to integrate this d phi. Integration d phi will be equal to R is constant, it will come out integration I into dt, and therefore integration I dt over here is nothing but the area under the curve equal to area of the right angle triangle. Okay, area of the right angle triangle. Here you can see the curve is a straight line right now. Okay, the graph shows a straight line. So if we want the integration I dt, then it should be nothing but the area of this graph. Okay, area under this graph. So we can easily find out this because it's a right angle triangle. So the area of the right angle triangle can be easily found out with a standard formula, isn't it? So integration I dt is equal to 1/2 into 4 into 0.1. Okay, we know that the area of a right angle triangle is nothing but 1/2 height into base, isn't it? So therefore, we have put the same numbers. 1/2 height is 4, then this is the base, that is 0.1, it is equal to 0.2. Okay, so this is the integration. Okay, and therefore phi will be equal to r into 0.2, and r is nothing but 10. 10 into 0.2 is 2 Weber. So the change in flux is nothing but 2 Weber. Okay, so therefore the correct answer is going to be option D, that is 2. Okay, 2 is the correct answer. So here is another question. An ideal gas transforms from state A to state B via 3 different processes as indicated in the given PV diagram. If Q1, Q2 and Q3 indicate the heat absorbed by the gas along the 3 processes, and delta U1, delta U2, delta U3 represent the change in internal energy of the gas in the 3 processes respectively, then which of these is correct? Okay, here it is. Q1 is equal to Q2 is equal to Q3, and delta U1 is greater than delta U2 greater than delta U3. Then Q1 is less than Q2 less than Q3, and delta U1 is equal to delta U2 plus delta U3. Then Q1 is greater than Q2 greater than Q3, and delta U1 is equal to delta U2 is equal to delta U3. And then last one is Q1 is equal to Q2 equal to Q3, and then delta U1 is greater than delta U2 greater than delta U3. So here are the 3 processes, as you can see. First one is this is second one, and this is the third one. So in these 3 processes, which one of these is correct? That is what we have to find out. So let's look at the solution. Okay, since in all 3 processes the system reaches from same state A to same state B, the change in internal energy is same in all 3 processes, as we have just seen in this diagram. Okay, over here the system changes from the same state A to the same state B. So therefore, what will happen? Change in the internal energy is going to be same in all these processes. So delta UA is equal to delta UB is equal to delta UC. That means in all these 3 changes, all these processes, the change is going to be same. Okay. Now we know the area under PV graph gives the work done by the system. So here we can see there are 3 processes. So area under this gives us the work done. So you can see here for this path the area is largest. So definitely the work done is largest in this case. Okay. So since the area under the graph indicated by path 1 is greater than the area under the graph indicated by path 2, which is greater than the area under the graph indicated by path 3, then according to the first law of thermodynamics, heat absorbed during path 1 is greater than that in path 2, which is greater than that in path 3, isn't it? So therefore Q1 is greater than Q2 and it is greater than Q3. Okay, so this is what is going to happen. So therefore the correct answer is going to be option C over here, Q1 greater than Q2 greater than Q3, and delta U1 is equal to delta U2 equal to delta U3. So this is the correct answer.